So I guess one of the most major pieces of work I've done was working out with a colleague of mine at Imperial College, Jenny Collier, working out how Britain became an island. And for this we did surveys in the English Channel, sonar surveys.
Right.
And we discovered this really bizarre landscape under the sea.
Right.
And it turned out that those landscapes were very, very similar to landscapes on Mars.
Welcome. AstroTalk UK is a not-for-profit podcast on astronomy, science and spaceflight. Launched in 2008, it's produced by me, Gurupir Singh, a writer based in the UK. I produce this podcast for my own education, but frankly, it allows me to meet fascinating people doing interesting things. It's primarily for my own education, and I share it as a free educational resource. No ads, no subscriptions, and you don't need to log in. For more, see the About page on astrotalkuk.org. Episode 102, Martian Geology with Professor Sanjeev Gupta. In 1972, Harrison Schmitt became the first, and so far only, scientist to walk on the surface of the moon. As a practicing geologist, he brought a scientific perspective to understanding lunar geology. Since then, many scientists have brought their scientific insights to understanding the surface of comets, asteroids, the planets in the solar system, and their moons. Professor Sanjeev Gupta is amongst the geologists helping to understand the Martian surface today. Not from field trips to the Martian surface, but from data returned by Martian landers, rovers, and orbiters. In this interview, recorded in July during COSPAR 2022, he describes his journey from revealing how the United Kingdom first became an island to making sense of the Martian geology.
Professor Sanjeev Gupta, you are a geologist by profession, but now you're looking at the geology on Mars. How did that transition happen?
Yes, I'm an earth geologist, and what I do is I study landforms on Earth, and I also look at rocks, particularly sedimentary rocks, and I try to reconstruct how the Earth's surface has changed through time, basically, through cycles of sea level change, climate, etc., and you try and reconstruct that. So it's a little bit like being a detective, that you look at rocks and try and piece that together. And my transition to space science and Mars was a series of serendipitous activities. So I guess one of the most major pieces of work I've done was working out with a colleague of mine at Imperial College, Jenny Collier, working out how Britain became an island. And for this we did surveys in the English Channel, sonar surveys.
Right.
And we discovered this really bizarre landscape under the sea.
Right.
And it turned out that those landscapes were very, very similar to landscapes on Mars. And formed by huge floods. So we have these things on Mars called the outflow channels, and they were interpreted from the Viking orbiter images to be due to huge floods on Mars about 3 billion years ago, something like that. And at that stage I knew nothing about Mars, but I accidentally came across some images of these features, and they looked exactly like the features that we see under the sea in the English Channel. And so actually our paper then we worked up was that actually Britain became separated from the European continent by a huge series of mega floods, which carved the same sort of landforms. And then that sort of led me becoming interested in Mars. And then the other thing that happened was that at that stage my children were quite young, and it was very difficult to go away and do field. So geologists go off into the wild, remote deserts and mountains I was kind of like, I was watching some of my peers, some of my colleagues, being able to do that, and I just couldn't do that because I couldn't get away for more than a few days because of childcare. And I was at a conference with a colleague who's actually here, also at COSPAR, and he had a poster next to mine, and he's a physicist, an engineer who makes images of Mars using, 3D images of Mars using, he's a technology expert, image analysis expert, and so he had a poster on how to make these images and data, 3D data, and I know how to interpret them. So we got on really well, and we just sort of joined forces, and that was my entry point into Mars.
How long ago was it that you did your work that I'm guessing that answered the question on how and when Britain became an island?
So our first work on that was published in 2007, so we've been working on that from about 2002 to 2007, and then we had a big paper in 2007. And then I would say that half the community didn't believe us, because it was high. These were the first images of. It was like looking at another planetary landscape. There was the first images of what the seabed looked like under the sea when you take the water away from sonar data. And then subsequently we started work on more detailed analysis, which was quite hard, and we had another paper in publication in 2017. In fact, it was quite amusing that our paper was actually published just the week before Article 50 of the Brexit thing.
Oh dear.
So we actually called it Brexit 1.0 because it was the geological Brexit, if you like.
Yeah. Fascinating, and that literally is, physical Brexit.
So, actually without that event, without that chance geological event, Britain would actually still be attached to the continent. There would be no seaway there.
It's an astonishing coincidence. But what's remarkable for me is how recent your work has generated this new information. The fact that this is how Britain became an island.
Yeah, we didn't know before. So people just assumed, we sort of almost assumed that it was just a slow erosional process.
And I know you said that you're really analysing sonar data of the English Channel that led to this revelation. So as a geologist, I'm sure you are no strangers to very strange and unusual places on the world where you go for your field work. But for this activity on the English Channel, or indeed elsewhere, do you actually go on scuba diving and look at...
Oh, no. So that was sonar data collected from a small boat. So a small part of the data was collected from a small boat for the project we had, but actually a large part of the data and the key data was actually archive data that had been collected by the government for civil safety at sea, but they hadn't sort of put it all together. And it wasn't interpreted as for geology basically, so it was all about civil safety at sea rather than scientific, and so we found a scientific use for the data, and it's extraordinary data.
Yeah, it's a little bit like decades ago when petroleum companies were scanning the seabeds in the oceans, and then later that data was used to understand plate tectonics to some extent. So you found a collaborator who was specializing in digital imaging, and you could of Mars. Do you, as a geologist, work on the large scale, the sort of hundreds and thousands of kilometer scale, or do you look at, some geologists do, through microscope at the little makeup of the minerals and grains of sand that tell you something about how...
So I work across all scales, and I guess what I would say is that I'm not an expert in one specific area. I tend to sort of jump around and explore different arenas. I was worried about that a little bit, because that means you're not a specific expert in something, but by being able to jump around and move fields and look at things at a range of scales, that gives you an ability to actually have a big picture view. So I'm quite interested in the big picture view. I like big ideas, etc. You need the small scale to test your ideas, But if you just focus on the small scale, you can easily miss the big picture. So I think you have to transcend across scales.
And that's been the story of science, and indeed COSPAR, this multidisciplinary approach, is what really delivers results in many, many instances.
Yeah, and all my research is multidisciplinary, crosses boundaries, etc. And that's what's exciting.
And how did you first, and what specific activity are you working with NASA, and particularly the rovers there?
Okay, so when I got interested in Mars, and we were working on a particular site on Mars, and somebody who was visiting my university said, "Oh, you do realise that that's one of the proposed landing sites for Curiosity." Actually, I didn't know anything about Curiosity rover at that stage. Right. So I actually went to one of these, several of these landing site workshops, and because my expertise from Earth is working on how we recognise ancient river deposits and ancient deltas, which is what people look for habitability on Mars. I was quite sort of outspoken about this at this meeting, etc., and gave talks about my experience from the terrestrial research, and there was a competition for people to join the rover team. So I wrote a proposal, and I was accepted. So I was able to join the Curiosity team.
So that Curiosity landed in 2012.
That's right. So it's almost 10 years now.
Yeah.
In a month's time.
Yeah, I think it's August the 5th. So when prior to it landing in 2012, how long had you been involved in, presumably, in selecting the landing position as well?
So I'd been involved for about 2 years 1 to 2 years in going to some of these workshops and giving talks about. So I didn't propose Gale Crater, which is where I was proposing another site, Eberswalde. We've never managed to get to my landing site, but yeah.
And from the data that now almost a decade old data, what kind of geological revelations have come out of that data from Curiosity?
So Curiosity's exploration of Gale Crater has just been, just changed our understanding of Mars. What Curiosity has shown is that Mars in its ancient past, 3.5 billion years ago, was a habitable environment. It's a place where, there was water at the surface on Mars, and it was persistent. It lasted for hundreds of thousands, if not millions of years. We had ancient lakes and rivers, and this tells us that it was an environment that life, if it was ever there, could have developed and evolved in.
Right. So your geologist eye tells you that in the past there was water there.
Yeah, so when you look at the landscapes, we look at those beautiful images that we have, and you see these landscapes, and that's what I'll be talking about on Friday here, is that you see this beautiful desert landscape that's really arid, hyper-arid and hyper-cold, but within the rocks exposed on the ground, when you look at the rocks, there are telltale signatures, clues, if you like, to a watery past, and that cannot be explained by this just forming in a desert environment.
And you're referring to those sedimentary layers.
That's right.
And the small pebbles which have been rounded through watering, and they are stunning images. It's incredible.
I know, the cameras are just extraordinary.
And it just, sometimes I forget that it's another planet. It looks so much like some parts of the Earth. It's just
I forget this because I look at these images every day, so it becomes a day job, and you forget actually you're looking at pictures from another planet.
So if you, as a geologist, are looking at the large scale, I guess most of the data that you would be using in your investigations is from orbiters. What kind of insight do landers and rovers provide you as a geologist?
So there's a huge scale difference, basically. So, the highest resolution we can see from orbiters, for example, with the HiRISE camera on Mars Reconnaissance Orbiter, we could probably see this table, this large table over here. That's several meters across. But the real details for geologists are at that meter to sub-meter scale, and the detailed textures in the rocks, etc., which are really the clues.
Right. And in terms of that's curiosity, are you working with data from Perseverance as well?
Yeah, so I'm on the Perseverance rover team also.
Right.
And actually for both missions, I'm also do a lot of operations.
Right.
So it's not just science analysis. I'm what's called a long-term planner. And there's a small group of people who work with project management and the chief scientists of the missions in, obviously these teams are huge. So how do you actually make decisions, etc.? So we work in helping the science team come to decisions about what we're going to do, what experiments we want to do, where we want to go to, what the results mean, coming to some sort of consensus view.
And in terms of the long-term plan, what can we look forward to that you might know about that will be coming to our screens in the near future? Or
yeah, so both missions, both the Curiosity mission and the Perseverance, are just really exciting at the moment. It's quite hard working on two missions, but it's really exciting. So Curiosity is exploring a transition in the rocks that go from rocks laid down in very wet conditions that have a lot of clay minerals, and then we see this chemical transition into rocks bearing sulfate minerals, which are less water bearing, and there seems to be some sort of, it seems to be a drying out basically, and the sulfate bearing rocks have signatures of deposition by wind, so rocks formed by sedimentary particles formed by wind, but we still see some signatures of water in there. So there seems to be some climate transition that's being recorded in those rocks.
Climate change?
Yeah.
So it's like climate change on Mars?
Yes, climate change on Mars, which is really exciting. So that's upcoming to see what actually happens with that thing. And we're just traversing through beautiful terrain. It's really amazing. The images are just gorgeous. And then, sorry.
So in terms of the chemical compositions, there's been a lot of evidence for a long time about the conditions for life in the past being present. Have any organic chemicals been detected? Yeah,
so Curiosity has discovered organic matter, so sort of moderately complex sulfur-bearing organic compounds. They've recovered these from mudstones that were formed in an ancient lake 3.5 billion years ago. It's amazing that we can actually even detect that. And that speaks to, so the organics don't mean life, because they could have been formed abiotically. The team think that they were likely delivered by meteorites to the Martian surface. But the fact that we can discover them and detect them, it's amazing. And then now what Perseverance is doing, so the Perseverance is now just exploring this beautiful delta that formed in an ancient crater lake at its landing site, Jezero crater, and we're just starting to explore the basal rocks, the delta rocks, again looking for fine-grained deposits that might contain organics.
And the delta at Gale crater is where really the most interesting part from a biology point of view, potentially. Is that?
Well, the trouble is we don't really know where we would find life on Mars and what it would look like. So I think it's difficult to say that. But using our Earth examples, yes, but we don't know. So, for example, we're going to spend the next year or so exploring the delta, and then we'll go out and explore the rim of the crater, and there's also these carbonate-bearing rocks in Jezero. And the reason that Jezero was chosen is there's a diversity of rock types, and so you can't put all your eggs in one basket, as the phrase says, so you don't know.
And Perseverance, of course, carried with it Ingenuity, this small helicopter. Has that informed anything to do with Martian geology in any way?
So I think Ingenuity is really a technology demonstrator. They want to demonstrate that it could get powered flight on Mars in this thin atmosphere. And it's a future in some ways of, so for example, when I do fieldwork on Earth, I routinely use drones just to get a different perspective on the rocks. So we use the images that Perseverance, that Ingenuity takes to get a different perspective,
right,
etc. But it's early days yet for this.
But it's, I mean, the kind of point of view you can get from Ingenuity is very unique and for the first time.
Yeah.
So early days, as you said, but it's been remarkably successful, and it's still going strong, of course.
Yeah.
In terms of any outstanding revelations of the Martian geology, is there anything you can point to that is a recent discovery?
So I guess the most exciting research results from other missions has been the InSight mission, which has detected Mars quakes, and it told us something about the subsurface of Mars, and that's really fascinating and exciting too. It's the first geophysics mission to Mars, and I think we've learnt about the deep structure of Mars, which is, again, a game changer. And then we've had a couple of orbiter missions which are looking at the atmosphere of Mars, both the Tracegrass orbiter from Europe and MAVEN, and they're telling us a lot about atmospheric processes and atmospheric chemistry. Obviously TGO is looking for methane, and so it's not something I know very much about, but it's quite exciting. It's an amazing time for planetary exploration at the moment.
And you mentioned methane. That was one of the early, going back quite a few years now, when methane was detected early on, and it seems to vary seasonally on Mars. There's two sources of methane. One could be biological, the other one is geological in some sense. So have you been focusing on that aspect of if it's a geological source, where the methane
So I think
might come from?
it's not something I do, but I think the science team for Curiosity, the people who work on that, have been trying to think about mechanisms, because the thing is that so Curiosity is detecting a transient methane signature, but TGO doesn't detect that, and they do joint experiments, etc. So it's a bit of a conundrum, basically. It may be that the methane is seeping up from deep underground through fractures, but because Curiosity is at the surface, it sees that, but then TGO doesn't see that in the upper atmosphere, etc. So it's quite bizarre.
The TGO is the Trace Gas Orbiter in the European Orbiter mission, and that's quite interesting. That's why you need that combination of on the surface measurements as well as from orbit. The scale of these things is so dynamic. Currently, so as you're saying, we've got these missions on Mars already. Are you involved with, are you aware of what's going to happen next in terms of exploring Mars?
So we have two big things. So firstly, sadly, of course, we were supposed to have the European Rosalind Franklin rover launching this year, and that was delayed because of the crisis in Ukraine. And hopefully it's going to go later this decade, maybe 2028. It's still an amazing mission, so we hope that will succeed and can go and land, and it's doing something very different to Perseverance. Perseverance is obviously collecting samples that will be returned by a future mission I'll talk about. But so we hope that ExoMars, the Rosalind Franklin rover, can go. And the other big thing that's happening that Perseverance is the first stage of is Mars sample return. So scientists really want samples to analyze in Earth laboratories. Whilst we can do wonderful things on rovers, it's really until you get them into Earth laboratories that it's going to be quite extraordinary. And so we're collecting samples, and I think we've collected 10 samples thus far.
I see.
And we will be. The subsequent mission is going to land on Mars, retrieve the samples, put them into Mars orbit, perhaps around 2028, 2029, and then in 2033 there'll be a subsequent mission that retrieves those samples and brings them back to Earth.
it's long-winded, but it's one way of getting. It's not an easy task to solve. Not an easy problem.
And there's a whole set of talks tomorrow on that here.
Just going back to the ExoMars, the Rosalind Franklin rover that's not going to go this year as planned. As an academic, as a scientist, you've been working on many projects in the past. I was very touched by the kind of impact that cancellation of the launch of ExoMars had for the people who've been working on that mission for years. What's the experience, the feeling within the academic community or the engineers and scientists who are working on that mission for such a long time? Because it must be extremely disheartening.
Yeah, it's very sad, particularly for the people who've really, spent many years designing the rover, designing the instruments, building it, and obviously, some people have been working it for many years and will not necessarily, they might be retired by the time that ExoMars actually lands. So I feel for them, but obviously, from my perspective, the political situation is so grave that we can't think about science at the moment, And we just hope that politically it resolves, and
And we are here at COSPAR. One of the interesting aspects of COSPAR is it was set up during the days of the Cold War. There are people here from all over the world, all the countries. And on Mars, right now we have an orbiter from the United Arab Emirates and from India, China. China has a rover there as well. Do you interact with other space agencies around the world in any way?
I don't really. I think my time just goes, it's so busy with just working with the science teams of the two rovers.
Right.
But it's exciting to see, other nations. Mars doesn't belong to NASA or ESA. It doesn't belong to anybody. It's for humanity to explore carefully. And I would say carefully. We must explore it carefully.
And that's another aspect of COSPAR. They have these planetary protection rules in place. Is that something that you get involved in, or as a geologist, in terms of forward planning for future missions, keeping Earth contaminants away from Mars is such an important aspect?
Yes, so that's a really major thing, and that's not something that I'm directly have expertise in, but we're aware of this, etc.
And then finally, for the next 2 or 3 years, do you know what kind of specific aspects of Martian geology you'll be looking at?
So I split my time. So I do half Mars work and half terrestrial work.
Oh, I see.
So I'll be working on results from these two rovers for the next couple of years, both Curiosity and Perseverance. As with Perseverance, we explore the delta, and with Curiosity, we're going to transition from what I was talking about, the sulfate unit, into some more interesting, maybe water deposited units. So that's going to be quite exciting. But actually, on the other side, I actually work in environmental sciences as well, and I think I'm quite broad, and I think that's quite important to keep a broad framework. So a big part of my research in the last 10 years has actually been looking at water issues in India. So I work on groundwater in India, and which is a very serious issue. So we use satellite data, but also on-ground data, and what I hope to have is a series of spin-off projects where we look at the impact of groundwater depletion on farmers and for agriculture, etc. And currently I have a PhD student who's looking at using satellite data to look at human presence and how that's affected by the interlinking between where populations live and the landscape and the geomorphology. And there's some very interesting linkages there.
I know I said it finally, but having gone from terrestrial geology to Martian geology, going back to what you were saying earlier about that multidisciplinary approach, you seem very comfortable in jumping to and from different parts of different aspects of. You're happy on Olympus Mons as you are on the Alps.
Yes, I think the secret is to be aware of your limitations and to find the right people to work with. So you don't try and, so I go and find the experts in other areas and work with them. And so so you may have a little idea that's interesting, and then you go and find the experts. It's not that you can do everything. That's not possible anymore. So yeah.
Professor Sanjeev Gupta, that's a fascinating conversation about how you particularly move about different aspects of geology, not only on Earth but within the solar system. Thank you very much indeed. Appreciate it.
Pleasure. Thank you very much.